Welcome to part 3 of this set of videos on the piezoelectric effect. Last time I ended a discussion of the early use of piezoelectrics by pointing out some of the limitations of the early ones. To give an overview, since piezoelectricity is the ability to convert mechanical stress to electrical voltage and vice versa, there are a few requirements for good practical use. Firstly, this mechanical stress will generally result in the expansion of the material. This expansion needs to be reliable. If I apply the same voltage to 1,000 actuators from the same production line, I want to see reasonably similar extensions. And I also have requirements on the size of movement from a given voltage. For example, if I want to use one to control the position of an object, and that position needs to be changed by tens of microns, then that's the displacement that must be able to be made, and there will be a limit on the electrical power the device is supplied with. So I need to be able to occasionally have large changes in displacement for small applied voltage, and occasionally perhaps the other way around. I want smaller, more accurate movements for the same voltage. I need to be able to tune this to what I want. Another major problem is manufacturing in different shapes, how to reliably and cheaply make piezoelectrics in many configurations, so circles of various diameters, hollow tubes, stacks, squares, complex shapes. This leads us on to synthetic piezoelectric ceramics. During World War II, synthetic ferroelectrics were discovered. These devices are also piezoelectric by definition, and they have far higher piezoelectric constants than the earlier natural materials. This means that for a given electric field, a larger mechanical strain is produced. So this already solves one of your key problems: the size of movement caused by applying a reasonable electrical input being very small. First, these materials was barium titanate, and now lead zirconite titanate leads the way as the material of choice for piezoelectric devices. Another advantage of ceramics can be shown by talking about how they're produced. Firstly, the raw material is wet milled to make many small particles. Then this is calcined, meaning it's heated in the presence of oxygen to produce the piezoelectric material. Material is ran through a mill again, this time with a binder added, and the resulting mixture can be pressed into a die. Crystals, on the other hand, would have to be cut to shape. However, these can be made with dies. This massively increases the ease of producing different shapes, especially shapes that are difficult to cut, and especially shapes that are difficult to cut in quartzes, which a lot of the natural piezoelectrics were. As you can see, this is set up for mass production. Remember this transducer I showed back in the first video? That's ceramic, and that can be mass produced very cheaply. Now compare the size of that transducer to the amount of material you can make with an effective mill, and think of the speed you could produce these with a large set of dies. These allowed the development of many more technologies, for example buzzers, piezoelectric igniters, as well as use in microcontrollers and micropositioning. So at this point I think I've said all I would like to about the history of the devices. So next time I'm actually going to talk about the practicalities of piezoelectrics. I can use these transducers, and I'm going to record a voltage and produce a vibrational output